I don't know. Okay, guys, here we go. We're going to look at inductive and deductive reasoning today. And there's a little bit of vocabulary we're going to start with today to make sure that we're all on the same page with what we're talking about. Yeah? You may. Start looking at conditional statements and using them to arrive at conclusions. Okay? So how those a little bit. So reasoning, let's define what that is. So the book gives for that is, it says, you use inductive reasoning when you find a pattern in specific cases and then write a conjecture for the general case. Okay, I'm going to say that again. It's when you find a pattern in specific cases and write a conjecture for the general case. Okay, so I'm going to try to put that more in layman's terms here. So look for a pattern and try to describe what is going on in general. Okay, that's inductive reasoning. So it goes from something specific to something general. Have you guys ever seen like I don't know if you've taken tests in the past, or sometimes people will do these little online quizzes to see what your IQ is and stuff like that. You ever done those on Facebook or whatever? I've done a couple of them. A lot of the IQ testing stuff involves this, where you'll see it'll have 3 or 4 different objects in a line, and it'll say what's the next one in the pattern or something like that, right? That's inductive reasoning. That's what that is. Okay. So yeah, question. Yeah. Yes? Yes, you may. An example here of inductive reasoning. Okay, so these 3 objects are thinking of a pattern. And then we're going to use inductive reasoning to figure out what is the next object in the pattern and then describe in general what's going on. Okay? So, what is the pattern? What am I doing here, Zach?
You're adding one to the top every time and one to the bottom every time?
So I've got this line that divides the circle into 2 pieces, and then I'm breaking up the halves into smaller and smaller pieces each time. Okay, that is one pattern that's happening. There are other ways of looking at this one too, Nate.
You're adding a line each time?
Another line each time that divides it up. Yep, that's correct. Yep.
Multiplying it by a half?
Multiplying it by a half? Actually, no. It works for the first 2, right? Think about the first picture here has 2 pieces. The next picture has 4, so I've divided it in half. But if I divide 4 pieces in half one more time, what do we have? We should have 8, right? And how many do we have? 6. Okay. So if we're thinking maybe instead number of pieces, how many pieces do I have each time? 2, 4, 6. So what's going on there? Right, you're getting 2 more pieces to the pie each time, okay? So the next piece of the pie should have how many pieces? 8. And should have how many lines? 4. Technically, if you're going all the way across, it should have 4. Okay. So the next in the pattern then should be this. 1, 2, 3, 4 lines. And if you count them up there are 8 little wedges in that thing. Okay, so as we were discussing this, we kind of came up with some different ways to describe inductively what's going on. Okay, we're increasing the number of segments, 1 each time, that are breaking up that circle. we're adding 2 more wedges each time as we go. We are 1 more wedge to the top and the bottom of that circle that got cut in half. So any way that you want to describe that, that's describing what's going on in that. And that's inductive reasoning. That got mentioned when we read the definition out of the book. It says, when you find specific cases and then write a conjecture for the general case. Okay? They use this word conjecture, which we're going to talk more about later. So we're going to go ahead and define it now. Okay? When I wrote down the definition for inductive reasoning, I said, describe what is going on in general. Okay? So, but they said use a conjecture. Okay? And what you guys were just doing here right now, when I asked you what is the pattern, you guys were formulating conjectures. A conjecture is an educated guess of what's happening. Okay? It's just a fancy way of saying an educated guess. So you're not just blindly throwing an answer out there like 5, I don't know. That's not a conjecture. You're using the information that you have to make an educated guess. So part of the homework, it's going to give you some kind of a pattern or some kind of a situation or whatever, and it's going to ask you for a conjecture about what's going on. So you're going to make a guess about what the pattern is or what the relationship is between the 2 figures or whatever it is that you're doing. That's a conjecture. Okay. So something else we need to define before we can really move on here is a counterexample. We talked yesterday. We're going to go ahead and actually define the thing now, though. A counterexample. What does it sound like it is? Zach? An example that is wrong? Not exactly. It doesn't mean the example's wrong. Yeah. No? Okay. What is the word? Think about what the word counter means. Nathan? Yeah, I said Nathan. No, sorry.
It's the exact opposite of what you want the example to actually be.
Yeah. Okay. So it's an example that's going to counter what you would expect to have happen. Okay? It's the opposite. So it's like, oh, this is supposed to happen? Oh, yeah? What about this? Did you think about this situation? Oh, yeah. Counterexample. Okay? That sort of thing. So it says a counterexample is a specific case for which a conjecture is false. Okay? It's giving a specific example of, hey, if you do it this way, it's wrong. Okay? So okay, so a specific case where a conjecture is wrong or a conjecture is false, however you want to say it, that's a counterexample then. Okay? Can we find a counterexample? Let's practice this for just a second. So let's say if a number is greater than 5, then it is even. Okay, I intentionally gave you a conditional I knew was false. Right? We can all agree with that. That's false. Right? Okay. So, because I wouldn't be able to come up with a counterexample if it was true. Because if it's true all the time, no matter what. So, can someone give me a counterexample? An example of a situation in which this is false? Abby. Nope, that's actually true. 6 works, right? So remember, if a number with an example that shows that this is wrong, right? So if I have 6, it's even. Oh, great. Okay, so that one actually works. Yeah. 37 would work. Right. and there are plenty of them. Giving a specific case where the conjecture is wrong. That conjecture is not true then. Okay? The conjecture that, oh, they must be even numbers. Well, what about the number 37? Oh, right. Yep. That doesn't work. Yes, Zach?
Could you have just said, for the counterexample, could you have just said any number that's odd?
Example is a example. It's a specific case. Okay? So you're going general on it, which is true. Any odd number would be wrong. But a counterexample, because all you need is one wrong, bad place, and the whole thing is out the window, right? You just got to give me one place where it doesn't work, and then you've proved it wrong. So powerful things, because we don't have that every single one of these odd numbers doesn't work. As soon as we have one that doesn't work, that whole conditional statement that I wrote there, we know has to be false, because it happens all the time. All right, that would use a counterexample. So more definitions. Deduction. Okay, deduction. Most of what you guys are doing when you piece together proofs is using deduction to do it. So it says deductive reasoning. Okay, and I'm going to read again what your book says on this one, and then we'll see if we can write a definition that maybe reads a little better. But so it says deductive reasoning uses definitions accepted from the laws of logic to form a logical argument. This is deductive reasoning which uses specific examples and patterns to form a conjecture. Okay? So the big difference there is, in induction, we're looking for a pattern and we're saying, hey, it kind of looks like this is happening. In deduction, I say, I know this is true, I know this is true. Because of those two things, this other thing has to be true, no matter what. Airtight. Okay? That's a mathematical proof. That's proving things in mathematics. We want no room for error in mathematics. So I know this thing is true all the time, this is true all the time, this is true all the time. If I take all three of those things, whatever, put it all together, I can show you that this other thing definitely is true. That's using deduction. It's not saying, oh, it kind of looks like it's doing that. Nope, it's definitely doing this because of these other things. Okay? That's okay? You know it's true. Yep. So, using okay. Yep, true all the time to form a conclusion. And there are some different ways that we can use deduction. And that's what we're going to talk about next. That's going to be kind of our focus the rest of the time today, is what are the different ways that we can use deduction to arrive at a conclusion that we know is definitely true. Okay? It's because those are the ideas that we're going to want to carry with us, because when you write a proof, that's exactly what you're doing, is trying to show for sure this is true. So there are two different laws of logic that deductive reasoning that we're going to work with, and that's the law of detachment and the law of syllogism. You don't remember the names, but I'll try how it works with them. Okay, so the law of detachment says this. P implies Q is true. So I have some conditional I know is true. And P is true. Then Q is true. Okay, so if I have a conditional statement, P implies Q, that I know is definitely true, if I can show some example of the hypothesis that is true, then the conclusion for that is also going to be true. Okay? Seen through like an example, so I'll do that next. Okay, so we have to assume that the conditional is true. So that's going to be my conditional statement, and we're going to assume it's true. Okay? Hey, we're not going to debate the afterlife for pets, okay? We're going to assume, for the sake of the example, that that's a true statement, okay? All dogs go to heaven. Now, I could take this, because it is a conditional statement, I could take this and turn it into an if-then statement, right? I don't need to for this, but I could. Okay? If an animal is a dog, then it will go to heaven, something like that, okay? So what we're going to use. Okay, don't overthink it. Okay? And all dogs go to heaven. My example. So what do I know about Fluffy? Fluffy's going to heaven. Awesome. Okay? That's the law of detachment. That's it. Okay? Shh. You have some sort of conditional statement. If you are given an example of the hypothesis, then you can assume that whatever the conclusion was for the conditional, it's going to have that example. Okay? So, my conclusion. Please stop. All right. So that's the law of detachment effect. Now, sometimes you're going to have something that looks like the law of detachment, but you can't actually logically conclude anything from it. So I'll give you another example here. I had to at some point. All right. So this other conditional we're going to work with now is if you like Star Wars, then you are a nerd. Okay. If you like Star Wars, then you are a nerd. Mr. Herrick's a nerd. So, can I conclude that Mr. Herrick likes Star Wars? No. I can't. I conclude that I like Star Wars because I'm going the wrong direction with it. Now think about it just logically, without being too redundant here. If Mr. Herrick is a nerd, that doesn't mean that I necessarily like Star Wars. I could be a nerd for some other reason. Maybe it's Star Trek. Maybe it's the fact that I teach math. I don't know. But the point is, I can't conclude that for sure, right? Remember, deduction. You reach a conclusion and it is for sure the case, based on what you had. I could make a conjecture, I could guess that it's because of Star Wars, but I'm using that logic backwards. Thank you. You may put your hand down. So if I backwards, if I had this, then yes. If the statement was, if you are a nerd, then you like Star Wars, if I'm assuming that's true, then I could say, yup, I like Star Wars. But because it's the other way, the logic works the other way. If you like Star Wars, then you are a nerd. Okay? So the conclusion is being a nerd. So if I give an example of the conclusion, I don't know. So there's no conclusion to this thing. No conclusion. We're stuck. Okay. The other law we're going to look at is called the law of syllogism. Yeah. Yeah. And this one we're going to use quite a bit, actually. And this one says, if P implies Q, and Q implies R, then P implies R. Think about it. If P leads you to Q and Q leads you to R, overall, P leads you to R, right?
Yeah.
This is kind of like a property of algebra that you studied last year. You probably studied last year. Anybody know what that property is called? Starts with a T. Okay, you don't remember. It's transitive property. Okay, let me state the transitive property for you and see if that refreshes anything. If A equals B and B equals C, then A equals C. Does that sound familiar? Okay, you've seen it before. But anyway, it's the same thing, right? This is essentially the transitive property of logic. Except with the algebra, it's when you're using the equal sign. In this case, it's using the implies thing instead. But it's the same idea. Okay. So, this. So, conditional statements to get this one started. So my first one is, if a triangle is a right triangle, then you can use the Pythagorean theorem. And my second statement, if you can use the Pythagorean theorem, then a squared plus b squared equals c squared. Okay, so we're going to use the law of syllogism here to cut out the middleman. Okay, there's a stop along the way that we don't need to take here. We can kind of take the logic from the very beginning to the very end. So what is going to be my conclusion here? Yeah.
Triangle is a right triangle, then a squared plus b squared equals c squared.
Right. It's your conclusion on this one is another conditional statement. It's an if-then statement. Okay. So our conclusion is if a triangle is a right triangle, then a squared plus b squared equals c squared. Okay, that's using the law of syllogism correctly. Correctly. Yeah. Yeah, that's right. Now, they might try and trip you up with this one too. Okay? It has to be set up in a certain way. Notice the conclusion of the first statement is the same as the hypothesis of the second, right? Now, what if they had taken those two sentences and wrote the first one second and the second one first? Then the logic would still work. Okay? It doesn't matter. However, if they took one of these two sentences and switched the hypothesis and conclusion inside one of them, then you're in trouble. Then you can't link it up like we just did these two. Okay? So really be careful of that. I'm going to do another example here. I'm not going to tell you if it's going to work or not. I want you to look at it and tell me if it does. Okay? See if we can actually form a conclusion using the law of syllogism on this or not. Something I've learned in my experience. If a man is smart, he says yes to his wife. another statement. If a man is smart, he likes football. People might disagree with that. I don't know. Anyway, so the point is, if we assume these two conditional statements are true statements, then what can we conclude, or can we not conclude anything? Yeah. We can't conclude anything. Okay? The reason we can't conclude anything, who can tell me? Somebody who's not. You already have. Yeah, you did one though. Jason. Well, we're okay. We're not looking at the individual statements and just thinking about, regular life and all of that. So just in general, the way that I've set it up, why is it bad? Why are we unable to reach a conclusion the way that it's set up? Somebody has not answered yet. You can keep them up as long as you want. Yeah, Jenny? How so? Okay. What if I had taken this first sentence and said, if a man says yes to his wife, then he is smart? Could we conclude anything then? Technically, we could at that point, and they still have nothing to do with each other. But by writing it that way, of making it so they do, okay, the problem with this one is actually the fact that they both have the same hypothesis. The key is hypothesis of one, conclusion of the other are the same. Okay? Right. This is a P implies Q, P implies R. That is not what the law of syllogism has in it. It's P implies Q and Q implies R. So the logic doesn't work out here then. So we got no conclusion. Okay. So I am good with what I need to do. You guys have the rest of the time to work on your homework then for today. All right.